So our next speaker is Rajeev Rastogi. He is the director of ML at Amazon. He used to be the VP of research at Yahoo India before. He was a fellow at Bell Labs, and he's a fellow of the ACM.
Is that fine? Yeah. Okay. So what I wanted to do today is talk about. I'll start off by talking about a few applications of machine learning at Amazon. So how we are using machine learning for different applications within Amazon, and then I'll dive deeper into a couple of 2 or 3 applications, get more into the technical aspects of them. So let's see. Is this okay? Yeah. So this slide is just a sample of applications of e-commerce. We're using machine learning extensively to improve experience for customers, sellers, and also improve the quality of our product catalog. We have over 200 million, close to 200 million products in our catalog here in India alone, and billions of products worldwide. And of course, we are also applying machine learning to many different types of data, right from text, images, speech, and so on. Let me talk about at very high level, few applications that are more relevant to India. So, for example, to deliver a package to a customer, the address of the customer is extremely important. And as you can see here, many times we get all sorts of addresses that we have to deliver to, addresses with very poor quality. For example, here you have some wrong PIN codes, there are spelling errors, there are addresses with no blank spaces, for example. And we use machine learning to correct a lot of this. We're also, for incomplete addresses, we suggest words or phrases that the that the customer can add to complete the address. Again, so we use machine learning extensively just to improve address quality. And then there are some mundane applications like packaging, just determining what package to put a product in. I mean, here there is a trade-off between the cost of packaging and the likelihood of damage to a product. So clearly, I mean, you can go with one extreme is really no packaging at all, and the other extreme are these big boxes. And there's a trade-off here. As you go to the right, the cost increases, but and the likelihood of damage goes down. So you've got to find the right place here for that specific product, where you're not going to have enough damage while you're reducing cost as well. This is an interesting application. Again, typically when users buy products, they browse through many similar products, right? You're buying a smartphone, you're going to look at a Samsung, perhaps Apple, a whole bunch of other Chinese brands and so on, and then you're going to buy one of them. So we look for patterns, behavioral data on how customers are, what are the set of products that get co-viewed a lot. So they're, looked at a lot in customer sessions, but not co-purchased enough. So, pairs of products that get looked at a lot within sessions, but you never see them co-purchased. So those are good candidates for substitutes. And we use substitutes many times to show low-priced products to customers when they are searching, or to show a product that's locally available that they can get very quickly. If many of the products are remote, we'll try and show substitutes that are closer that can be delivered quickly. And of course, when the certain products are out of stock, we will try and show substitute products. Of course, we've done a lot of work on recommendations. There's a widget which shows products, customers who bought this also bought. This was again done way back and in the mid-90s, and it's essentially, the challenge here is really computing pairs of products that are frequently co-purchased at a scale of billions of products. So I think the key challenge here is scale, and how do you do that very efficiently, computing pairs of items that are co-purchased. And of course, we also learn about customer preferences based on their browsing patterns and purchase patterns, and then recommend products that match their preferences. Another interesting application, more on the seller side, is trying to forecast the future demand for each product. And this is extremely critical on the retail side. These forecasts need to be very accurate. If you forecast the demand to be too high, then as a retailer, you're going to be stuck with excess inventory that you have to store and potentially liquidate if it doesn't sell. On the other hand, if you forecast the demand to be too low, then the product is very likely to go out of stock, and this is not going to lead to a great customer experience. So again, the challenge here is there are many products that really have very few purchases. In fact, there are a small set of head products that get most of the purchases. Most products have very few purchases. Many of them actually zero. So being able to do forecasts for new products and products with very little historical data is extremely challenging. Product classification, again, I mentioned that we have close to 200 million products. We have to classify these into a product taxonomy, which has over 50,000 leaf nodes. So this, again, is a very massive multi-class classification problem of trying to figure out where a product belongs in the taxonomy. And customers typically browse through the product taxonomy to discover products. So getting accurate classifications of products is very important for discovery. So here you can see on top is the path, root to leaf path in our product taxonomy where this product is. When many sellers, we operate a marketplace, so many sellers may list the same product. So if you have many sellers who list the same product, you end up with duplicates or near duplicates in the catalog. So here's an example where all these products actually refer to the same real world products, but you can see that the images are not all the same. Also, the titles are quite different. There are variations in the titles. So again, we want to try and identify and eliminate duplicate products from our catalog. And this is important for certain applications like search, where you don't want to show duplicates in the search results because that's going to lead to poor customer experience. The last application I just wanted to quickly touch on is really about extracting fine-grained ratings for product attributes from reviews. So, and again, here we use natural language understanding, sentiment analysis, and so on. So here I've shown a screenshot of a website called DP Reviews, and it's DP Reviews is more, specializes in cameras, and it provides you fine-grained ratings for camera attributes. So for example, here you can see different camera attributes like image quality, performance, video mode, ISO performance, and so on. And these ratings on DP Reviews are all manually generated by experts. So you can see some of the experts up here. And what we want to do is automatically generate these fine-grained attribute ratings by extracting them from product reviews. And in fact, a lot of that information is already in the product reviews for many of the products that sell quite a bit and that have quite a few reviews. Okay. With that, let me just go a little bit deeper into three specific applications that my team here in Amazon is working on. One's on question answering, another one on catalog quality, and product size recommendations. So again, our product pages have a lot of information on them. We have product descriptions that contain information about product specifications like what's the battery life of a smartphone, or how many camera megapixels it has. There's customer reviews. These capture user feedback and sentiment about different product features. And of course, we also have, interestingly, customer QA data that contains authoritative answers to customer asked questions. So these are typically open-ended questions about that people ask about people's experience with using a product or how a product may compare with other products. Now, the average product page for the top 20 best-selling products across different categories contains around 4,000 words. So, that's quite a bit on a smartphone. And so it's quite difficult for people to find information that's in these product pages, especially when they're using smartphones. So, to make it easy for people to find information that's embedded in, product descriptions, customer reviews, community QA, and so on, we've implemented a question answering interface on our product pages. So you can go out here and in this box and type out your questions. So this is a sort of a screenshot of what our question answering interface looks like. Now, we looked at the sort of questions people typically ask, and what we found is, majority of product questions are about product features. So these can have factoid answers that can be directly extracted from product descriptions. So for example, here's a question, how heavy is it? And this has a factoid answer, 8.6 ounces. And or in many cases, these can have more subjective answers that are contained in product reviews. So for example, here you have a question, is it expensive? And the answer is extracted from a customer review, which says, for the price, the camera is a good value for money for an amateur. Right? Now, one of the things to observe here are that these snippets that contain the answers to the two questions do not really have high text similarity scores or high text overlap with the questions. For example, the question here had the word heavy, and the snippet here has the word weight. And similarly, the question here has the word expensive, but the snippet containing the answer had the phrase value for money, right? So what that means is you can't just do with simple text matching. What you need here is semantic matching, right? Of course, there are other types of questions. There are product comparison questions that compare two products with respect to certain features. We also have people also ask compatibility questions. So this is about how well a pair of products work together. So for example, here's a question, is it compatible with Canon lenses? So it's asking whether a camera works with camera lenses. So what are some of the challenges? Of course, a key challenge is understanding the semantics of questions. The question, what is ISO, refers sort of to the definition of ISO, but the question, what is the ISO, refers to the ISO value of the camera. So just a word inserted in there sort of changes the semantics of the question. Also, as we saw earlier, we need to perform semantic matching between the question and snippets, because there may be very few overlapping keywords between the question and matching snippets that contain the answer. And this is, again, because customer questions and review snippets can refer to a product attribute like price in several different ways. Cheap, inexpensive, bang for the buck. These are all different ways of referring to price, and matching these different variations of meanings, again, requires semantic matching. We want to generate natural language answers. So for example, for a question, is this expensive? A possible answer could be, this is great value for money. You want to answer questions with a high degree of precision. The system that we've deployed in production has a precision of greater than 90%. Of course, users can ask all sorts of questions. The data that may be required to answer some of these questions may not be really available, on your product page. For example, here's a question: will the suitcase fit in the overhead of an airplane? And unless somebody has already answered that question, you need access to the dimensions of the overhead of an airplane, which you may not have. And in many cases, there are also data quality issues. So the data that you may have on the page may not be accurate, and this could lead to incorrect answers. So to find these semantically matching snippets for a user question, we learn joint embeddings for questions and snippets so that semantically related questions and snippets have embeddings that are close or similar. And embeddings here are nothing but mappings to a high dimensional space. We learn these embeddings using a Siamese neural network. This is, again, an example of a triplet network, which is trained on question, relevant snippet, and irrelevant snippet triples. The way we go about generating these training examples is using our community QA data. So the question answer pairs that we have in our community QA data become the question relevant snippet pairs, and then we select these irrelevant snippets either using random sampling, or we have some better schemes of selecting hard examples, hard negative examples to create these triplets. And word embeddings of, so here, for example, the question is it expensive? The relevant snippet is the product is very good for the given price. And this is an irrelevant snippet. Autofocus is great. And word embeddings of these, of the question, relevant snippet and irrelevant snippet are fed into 3 separate recursive neural networks that generate these sentence embeddings for each of them. Okay, so the word embeddings, again, are computed using word2vec. This finds vector representations for words based on contextual similarity. And the question embedding is then combined with each of these snippet embeddings in an additional layer at the top that outputs the probability that the snippet is relevant to the question. This here is modeled by a logistic function applied to the dot product of the embeddings. We also consider a case where this layer generates the cosine similarity between the question and snippets. We consider several, okay, wait a second, what happened here? Yeah, so we considered several different loss functions that are minimized to learn the question and snippet embeddings. The first loss function is simple log loss, negative log of the product of probabilities of the relevant and irrelevant snippet. The second loss function is the triplet loss, which is the standard loss for Siamese architectures that was proposed by Wang et al. In their 2014 CVPR paper. And what this loss function tries to do is maximize the difference between cosine similarity scores of the question with respect to relevant and irrelevant snippets. The loss function imposes a penalty if the difference between cosine similarity scores drops below this threshold m, and once the difference exceeds m, the loss function value drops to 0. And we had some other loss functions of our own also that we experimented with. The metric that we used here was precision at rank 1. Again, precision at rank 1 measures the fraction of times that the snippet with the closest embedding to the question embedding is relevant. And as you can see here on in the table, of course, the baseline here that we used was simple text matching based on cosine similarity. Just looked at simple cosine similarity between question and snippet text. So we had some interesting results. You can see that the baseline scheme that is based on cosine text matching and simple cosine similarity has the worst performance. In contrast, our semantic matching approach that learns these embeddings using loss functions has a much higher precision at rank 1 score, all the way up to 96%. So that's one key takeaway from this slide that, semantic matching does give you better performance. Another takeaway is the choice of loss functions is quite important. So here you can see that using Siamese loss that tries to increase the margin between the cosine similarity scores does a lot better than simple log loss that tries to minimize the negative log likelihood of the data. So just moving on to some qualitative results. So here again you can see that our question answering system returns semantically matching snippets for the first 4 questions. It figures out that the word basketball in the first question is semantically related to the word sports in the matching snippet. Similarly, the word price in the second question again is semantically matching with the snippet that contains the word cost. Similarly, the question, how big is it, is semantically matching with the snippet that has item dimensions, and so on. Of course, our question answering system does make errors. So for example, for the question on how much weight can it hold? So this is about, again, how much weight can the camera tripod hold? It erroneously returns the weight of the camera tripod instead of the weight that the tripod can hold. So again, in many cases, the snippets in the reviews can be long and they can contain multiple attributes. So for example, here, this snippet talks about both video and price. And if you have a question about video, so for example, how is the video quality? Only the portion of the snippet pertaining to video is relevant here. And so we want to combine the embedding of the question embedding with the embedding for the relevant portion of the snippet. And here we can do this using an attention framework that was proposed by Badana and in this ICLR paper in 2015. So what this does is this adds an extra layer on top of the LSTM layer. This layer computes a weight alpha I for each hidden state hi of the snippet, and then computes a weighted sum as shown here of all the hidden states. And these attention weights, alpha I, are proportional to the similarity between the question embedding and the hidden state hi. And so again, these attention weights are proportional to the capture the relevance of the words to the question embedding. And you can see here again that for the question, what is the price? Words like expensive that are related or relevant to the question get higher attention weights. So with that, I want to talk a little bit about catalog quality. As I mentioned earlier, we have a catalog with hundreds of millions of products. There's a lot of metadata in the catalog related to titles, images, descriptions, and users browse through the catalog to make purchase decisions. So that it's important to make sure that the information is factually correct, that the information across different attributes in the catalog is consistent, and they also adhere to set guidelines. Now, in our catalog, the information is typically entered by sellers, third-party sellers who sell on our marketplace. So we don't have a whole lot of control over the information that's input. So in many cases, product listings end up having defects, and many of these defects can again hurt sales. They can lead to excessive returns and so on. And so we use ML here to identify and fix defects at scale. So here's an example of defects that people enter in our titles. So for example, here you can see that this title is extremely long. It also contains various spam keywords like Bollywood and designer, beautiful, latest design. I guess a lot of people search for Bollywood, and sellers want their products to show up, in those queries, and so they put in these spurious keywords. Some sellers even put in their email IDs in the titles. And again, we don't want contact information in the titles. The title should be, really about the product, capturing the most important attributes of the product. We have many projects around, how do you build titles, very effective titles. We analyze search queries that users do. We see what attributes users are searching for to try and figure out what are the most important attributes as far as users are concerned. So we have a set of mandatory attributes for every product, which are all, again, determined based on data. Search queries, reviews, what are, how correlated is the sentiment on certain attributes with the ratings for the reviews that users are giving. So there's fairly advanced schemes that we use to determine what attributes should be in the title. Again, there's lots of different image defects. Here, the background is not white. That's one of our requirements, one of the guidelines that we have. A lot of times, there's also images with celebrity faces. Priyanka Chopra is quite a favorite for modeling clothes and so on, and it's all unauthorized use. So, identifying celebrity faces within images is also important. Here, the image is sort of cropped, doesn't show the complete product. And of course, there's also defects of the kind where there are mismatches between the title and images. So for example, here you have a title that says the product is a t-shirt, but the image shows, a bag. Similarly here, the title says the color is blue and the image has a pink dress, right? So, again, a key capability to detect such defects and fix them is the ability to extract attributes from text, like product titles and descriptions. For example, here's a title. We want to be able to extract brand and color. And we do this using recursive, deep neural networks. The title is input into a multi-layered deep neural network, and embeddings here that are generated by this bidirectional LSTM layer are input into a CRF layer as features that then outputs labels for the different words in the title. Another important capability is the ability to detect image defects, extract image attributes, such as color. So be able to say, like this dress here in this image is red. Be able to classify images. So for example, this image has a t-shirt and it belongs to the apparel category. This is an image that is of poor quality. So we use, again, deep convolutional neural networks here to learn image representations that are then input into ML models for these different classification tasks. And of course, once you've extracted different attributes like brand, color, category, and so on from the title and image, you can compare them. If you find that they don't match, these extracted values don't match, you tell the seller that they've got to go and sort of fix this defect. So the final topic that I want to talk about is product size recommendations. And the problem here is to recommend the product size that would best fit a customer when the customer visits a product page. And this is especially important in categories like apparel and shoes, where really brands don't have standard conventions. Different brands may have different sizing conventions. At the bottom of the slide here, I've shown the mapping from catalog sizes to physical sizes for two popular brands, Reebok and Nike. So you can see that, a catalog size 6 for Reebok corresponds to a physical size of 15 centimeters, but catalog size 6 for Nike corresponds to a physical size of 16 centimeters, right? So depending on the brand, depending on the type of shoe, the catalog size that may fit a user could be very different, right? And this is one of the reasons why in shoes and apparel categories, people a lot of times will buy the wrong size when they're buying online, or in some countries we've seen people will buy 5 different sizes and keep one that fits them and then return the rest, right? So in general, one of the problems that we have is that these products have high return rates due to fit issues. And of course, when we have a lot of returns, that adds to costs because we're shipping products out to the customer and then it's coming back. So again, so what are the challenges here? It's again, hundreds of millions of customers and products. There's data sparsity, as I mentioned earlier. A bulk of the products and users have very few purchases, right? So only a small set of users and products account for most of the purchases. There's cold start scenarios involving new customers and products. And so we leverage a lot of user features and product features here to deal with cold start. And a unique problem here also is that a single customer account may have purchases for multiple different people and personas. So you can easily imagine, family members sharing an account, and all these personas may have very different and varying sizes. So our approach here is to learn the true latent size. So this is something that we don't know. What we see is the catalog size of products, right? The true size for a product or the true size for a customer are in fact latent. So the true size for a customer is simply corresponds to the physical size of the customer. In this case, it would be the feet size. The true size for a product corresponds to the physical size. Here, I'm just taking it as a one-dimensional quantity, but size, you can imagine, could be a multi-dimensional vector. So it could be the width, length. Shoes can have 20 or 50 parameters, but the techniques we have can be generalized to multi-dimensional. So, and what we're going to do is leverage to learn these true sizes. We're going to leverage past customer transactions. Each transaction is a triple IJ, YIJ. I is the customer, J is the product, and YIJ is the transaction outcome, which can be one of its ordinal values, which can be one of small, fit, or large. So here in this table, you can see customer 1 finds Adidas size, catalog size 9 as large, but a Reebok catalog size 8 fits the customer, right? And the problem we have is to say, well, what if the customer tried a Nike size 9? What would be the outcome? Would it be a small, fit, or a large, right? So that's sort of the problem setting. And here's some notation. The latent size for customer I is, again, something that we don't know. We're going to represent it by SI. The latent size for product J is TJ. And the catalog size for product J, which we know is going to be CJ. And what we are going to do here is model the probability of fit, which is shown here as a function of the difference between customer and product latent sizes. So if the difference between customer and product latent sizes and customer and product latent size is 0, that means they're equal, then clearly you want this to be large. The probability of fit is going to be large. But if the difference between the customer and product latent sizes is large, right, then you want this probability to, again, come down. So you want that probability to be low. And once you have a way of estimating these probabilities for a customer I, you simply have to recommend the product J that has the highest fit probability. Okay. So we're going to use a Bayesian modeling approach here to both estimate the latent sizes as well and the fit probabilities. Again, as I mentioned, we have data sparsity. So by placing priors on latent size variables, we're going to, the priors are going to help to prevent overfitting and help to regularize these latent sizes. Another advantage is that we can model uncertainties. Your posterior distributions capture the uncertainty in these latent size variables, and then by marginalizing over these posteriors, we're able to capture this uncertainty in the final fit probability scores. One thing you're going to see is these models can capture all the available signals that we have, and that's really in one framework rather than doing it separately. So, we can capture all the, we have ordinal transaction outcomes, we have features of customers and products, and then we have hidden variables. We have customer personas and latent sizes. So all of this can be thrown in one generative model, and we can, do Bayesian inference for everything jointly. And so that's, again, a really nice, elegant and principled way of doing inference. And of course, one of the disadvantages of Bayesian techniques is that in many cases, the posteriors do tend to be come out to be intractable, and it's going to be the same way here. But there are efficient techniques for approximate posterior inference using Markov chain, Monte Carlo, and variational inference methods. So here's just the intuition. If we have a transaction IJ fit in our data, it means that SI with high probability lies in this small range around TJ. If we have a transaction IJ small, then with high probability SI is the customer size, right? And TJ is the product size. So, if you have an outcome that's small with very high probability, SI lie to the right of TJ. So SI must be much larger than TJ. And if we have the transaction IJ large, then with very high probability, SI must be to the left of TJ, right? Now, we can capture all this intuition in these the data likelihood functions for the three ordinal outcomes, small, fit, and large, and these are shown on the slide here. So, and they involve products of logistic functions of the difference between SI and TJ, right? Difference between the customer size and the product size. As I mentioned earlier, we want the probabilities for fit to be proportional, to be a function of the difference between the customer and product latent sizes. So, Albert and Cheap, in fact, had first proposed a Bayesian treatment for ordinal regression problems, but in their 1993 JASA paper, but that was more for probit likelihood functions. So we are going to model this using logistic functions and use a different optimization framework to infer the posteriors of customer and product latent sizes. So you can see here if the customer latent size SI is much larger than the product latent size TJ, then this term kind of goes down to 0, and the probability that the transaction outcome Yij equals small, the probability of that outcome is close to 1, which is exactly what you want. When the customer latent size is much larger than the product latent size, you want the probability of the transaction outcome being small to be large, right? Close to 1. On the other hand, if in this case here, if the product latent size, TJ, is much larger than the customer latent size, SI, so then you can see that the probability that the transaction outcome here equals large is going to become close to 1, because both these terms here will become close to 0, right? And that's exactly the outcome you want. When the product size, latent size, is much larger than the customer latent size, you want the likelihood that the customer is going to say that the product is large is going to be close to 1. Okay, so I'm running out of time. I'll just speed up a bit. Do I have 5-10 minutes? Okay. Yeah. And of course, similarly, you can see when the customer latent size and the product latent size are close to each other. Here B1 and B2 are constants. B1 is a positive constant. This is a negative constant. So these become close to 0. And again, this quantity again starts becoming close to 0, and probability of Yij equals fit starts becoming, gets closer to 1. And one can show that the sum of the probabilities of small, fit, and large add up to 1. Okay. So now, this is data like, and this is how it sort of looks when you plot it. And again, you can see, the probabilities of small, fit, and large. Here, large is the blue curve, when SI, which is again the customer latent size, which is much smaller than the product latent size, then you want the large probability to be 1, close to 1. And you can see that sort of what's happening here. And then when, as you increase the customer latent size, SI, as that keeps increasing, the large probability goes down and the fit probability starts going up, which is this green curve. And the fit probability is maximum when SI is equal to TJ, which is exactly what we want. It's close to 1. And then, as SI increases beyond TJ, the fit probability starts going down and you start seeing the small probability go up. So this likelihood function behaving exactly, intuitively the way we'd like it to behave, right? So now here's the generative model. So we place these Gaussian priors on the customer and product latent sizes. The mean, the product mean size is selected, is initialized to the catalog size Cj, which is what we know, and the customer mean size, this quantity mu I, is initialized to the average size of products that are purchased by customer I. Okay, so that's how we initialize it. And then for a customer I and product J, we select the transaction outcome Yij, again, with probabilities that were given by the likelihood function in the previous slides. Okay, so that's sort of our generative model, simple generative model. And now we want to do Bayesian inference, which involves estimating the posterior distribution of the customer and product latent sizes, which again, by Bayes' rule, shown here is proportional to the product of the data likelihood and priors. So, a beta here is the vector of latent sizes. S1 through SC are the customer latent sizes. T1 through TP are the product latent sizes. So, the data likelihood here is the product of all the probabilities of the transaction outcomes, which consist of logistic function terms. So the data likelihood is the product of logistic terms. One can simplify it, so a product of logistic terms over XY pairs, where Y takes value 0, 1, and X is a vector with alpha and minus alpha in positions of SI and TJ, assuming that this term has come from a transaction IJ, Yij, right? And you have some constants at the end. Now, this is not, the posterior distribution is not available in closed form, again, due to these logistic likelihood terms and these normal priors. And so we use Markov chain Monte Carlo methods here to approximate the true posterior. And to make this posterior tractable, we use rely on data augmentation techniques for fully Bayesian and inference in models with logistic likelihoods. This was proposed by Paulson et al. In their 2013 JASA paper. And the idea here is to introduce these augmentation variables. So specifically here we add Polya-Gamma latent variable W for every XY belonging to D. And XY were those terms for those logistic functions. And if this is the joint likelihood, one can show that the integral of the joint likelihood is in fact a logistic function. So you can simply replace the logistic functions in your data likelihood by these integrals here, right? And so what you're going to end up getting is that the posterior now of customer and product latent sizes is proportional to the integral of this augmented joint data distribution. So you have, it's augmented because you've added these Polya-Gamma variables. So you can now approximate the posterior by approximating just the this quantity in the integral. And this quantity here, the augmented joint distribution, is this big term here, right? And you can derive closed form equations here for the conditional distributions. For this particular term, you can get closed form equations for the conditional distributions of both Wi, the Polya-Gamma variables Wi, and the latent sizes beta j. So the conditional distribution for Wi is another Polya-Gamma distribution, and the conditional distribution for beta j is a normal distribution with mean mj and variance vj shown on this slide. And you can use a Gibbs sampling algorithm here now to cycle through these Wi and beta j variables, drawing samples for each of them from its distribution conditioned on the values of the different variables. And one can then average over all these samples to get the predictive distribution for fit probability. Okay, just a quick some experiments that we did on real life shoes data sets in Amazon. And here we compared our scheme with a baseline model that simply sets the product latent size to the catalog size and the customer latent size to the average size of products purchased by the customer, and trains a regression model to predict the outcome with feature Si minus Tj, right? And our Bayesian logit model tries to predict the outcome with has the highest probability after averaging over the samples that we had of the customer and product latent sizes. So here again, you can see that the improvement that we get in weighted AUC using our Bayesian logit model over the baseline model can vary from all the way from 17% to 26%. Okay. So I guess capturing some of the uncertainty, introducing the priors, sort of helps our algorithms cope with data sparsity issues and so on. And as I mentioned earlier, the nice thing about our model is that we can really expand it further. So for example, in many cases, we do have information about customers and products. So we have customer features, their age, gender, location, and so on. We have also information about products, the product type, title, brand, catalog size, and so on. So all of that we can leverage all that additional information to handle data sparsity and also deal with new products and customers. Incorporating these features into our model just involves performing a regression on them to obtain the means of latent size of the priors of these latent sizes. So for example, here, in our generative model, we draw these customer latent size, the customer latent size SI from a Gaussian with mean, WF, Fi. Here, WF are the regression weights. Fi is the feature vector for customer I, right? Earlier, we had simply initialized that to the average size of products that the customer bought. Now we just do a regression over the customer features to sort of get the means, right? And similarly here, we draw the product latent size Tj from a Gaussian with mean Wg, Gj, where Wg are the regression weights and Gj is the feature vector for product J. And here again, one can use a Monte Carlo EM algorithm to learn these regression weights. So once you've approximated the posterior of customer and product latent sizes with these samples, from the posterior using Gibbs sampling, In the E step, in the M step, you perform a least squares regression to learn the weights WF and WG, right? So that's nice. You can even throw in the customer personas. We maintain a new latent size variable SIK for each persona K of customer I. We also introduce a new latent variable Zij that captures the persona that's involved in transaction Ij, Yij. And now at the start in our generative model, you draw a persona distribution theta I for every customer I from a Dirichlet distribution with concentration parameter alpha. For every transaction Ij, Yij, you first draw this persona Zij from the multinomial theta j, and then you again draw your transaction outcomes with probabilities given by the likelihood functions that I defined earlier. And one can easily show that our Gibbs sampling algorithm can be extended to draw persona samples for this latent variable Zij. So just to summarize, I talked about many different applications, and in all of them, we were at some level learning some semantic representations of the data, whether it was, embeddings for questions that we talked about here, using deep learning to learn these semantic embeddings and then using them to match questions and snippets. In the product size recommendation problem, we were using, again, probabilistic graphical models to learn these latent sizes. Of course, in the deep learning case, we saw that choice of loss functions is important. Siamese loss did a lot better for us than using just simple log loss. Of course, with the Bayesian techniques, we did get better results due to having priors that help prevent overfitting and also help to handle data sparsity. You had posteriors that captured the uncertainty in the data. And I think one of the biggest benefits of these probabilistic graphical models was the ability to capture so many different signals and so many different aspects of the problem in a single generative model, and then do joint inference for everything. So with that, I'm happy to take questions, and thanks.
Hi. So I had a quick question. In the persona identification problem, at the time of purchase, so at inference time, so you mentioned that there would be another latent variable drawn to indicate which particular persona is making that purchase. How is inference done for that? Is it contextual information, time of day, or something? Because any given persona could have been making that purchase.
Right. So again, once we have, we may have some context because the user may have browsed something, right? So I think given some history for the user.
Immediate history.
Yeah, immediate history. So you may have some session information on what they browsed previously, and then based on that, you can infer which persona may be active. And then given that additional data, you're trying to predict what would be the size that you want.
So we have not reported it, but this is making a continuity assumption that when one is making purchases for a certain member of the family, it continues. But I mean, I often...
typically it's the case, the person who's browsing, yeah, of course, you're saying, well, if there was somebody making purchases for many different people in a single session, right? But typically, I think there is continuity, there is temporal continuity, I think, in the way people browse. When they are, maybe, it's not true for you, and it may not be true in every case, but there is typically temporal and spatial continuity here.
Because in my family, if I am on Amazon, my dad will say, "Oh, can you order this for me as well?" And my mom will, "Oh, can you order this for me?"
Yeah, we use behavioral data a lot. I talked about substitutes, right? It's all based on within a single session, what are the products that you, and there is, we have seen, and of course, there's always noise. So you use certain thresholds to filter out cases. But there is a case where people will browse for similar products when they are shopping. So we do exploit a lot of behavioral data.
Yeah, hi. Actually, I wanted to know more about probabilistic graphical model, the Bayesian model you're using.
Right.
You're going with Monte Carlo methods, and then perhaps you are using predictive distributions.
Yes.
Have you heard something like of structured learning for probabilistic graphical models?
So in what sense? I mean, structured learning of...
The Bayesian model.
Right.
If you learn and predict like that, an alternative approach. Have you thought like?
No, we haven't explored that. I think this again, this is the model that seemed to fit, the specific sort of data that we had. So we had ordinal outcomes. So we needed somehow to handle ordinal regression case. And, so I don't know the alternative methods that you're talking about. Maybe we can discuss that offline. I'm interested in knowing more about that.
Even I am.
Hello. So I have a question here. So I can see that you have very carefully designed the likelihood function so that it fits the intent of the problem. Yeah. So I was wondering if, did you try using a neural network instead of having this logit function? So if you pass, then...
I mean, we can use a neural network probably to, the part here, I think, this function here, instead of being a linear regression, we could perhaps replace that with a neural network.
I mean, you keep the entire model as a Bayesian model with a prior and do the posterior inference, but instead of having a likelihood function carefully designed, you just pass it through a deep neural network and...
Right. Yeah. I mean, that's a good suggestion. In fact, I think I was talking to somebody from Mintra and they used a neural network and it did better than this technique. So, yeah.
Thanks.
Hi. My question is about the product categories. So do you control it completely from your side? So how it evolves? Or you let sellers create new categories or you try to infer new categories from the data?
Which problem are we?
So I'm talking about the product catalog that you talked about. But within that, the new categories of the product. So do you manually create them new or you let the sellers add the new categories or you try to infer new categories from the data that...
Oh, the taxonomy is something that we provide.
Okay.
Sellers cannot change the taxonomy. But sellers put the products in the taxonomies. But the categories and the taxonomy is something that we own. The sellers cannot change the taxonomy.
But taxonomy, so you do not try to infer the taxonomy,
right? I mean, like apparel, electronics, then smartphones, laptops. So there's a
higher
whole
levels,
product hierarchy, right?
Yes.
That we provide. And then sellers are supposed to, ideally put their products in the appropriate leaf node. And in many cases, the sellers, can't do it right or just don't do it. And
my question is about the fine grain. So categories, they would almost remain same, no changes. About the fine grain categories, they might evolve over time. So you still change them manually or you try to infer them from the product description?
Done. It's manually changed. It's all manually done. We don't, I mean, one could look at looking at co-purchases and things like that, and then trying to use behavioral data to infer the entire taxonomy, but that's not something that Again, those are very noisy. I think we have to manually curate taxonomy to maintain quality.
There are no more questions, then let's thank the speaker again.